Okay, time to get started. And the first thing, I had to turn to make sure I have the right thing on the screen this time. First thing I want to do is to remind people that we have our first exam a week from yesterday. So people will probably want to know what's coming up. So I have just some things here. It's going to be covering chapters 1 through 3. I'm going to finish off talking about chapter 3 today. So today will be the last piece of material that will be on the exam. So you have some time to review it. It won't be just fresh material. It'll be stuff you've had time to review. There'll be 10 problems, roughly evenly split between conceptual and calculation. If you look at them, it will look like there are more calculation problems than conceptual. That is, there are problems with a bunch of numbers on them. But some of the problems with a bunch of numbers on them are not actually calculation problems, right? And so if you're doing calculations on them, I suppose you could try to do calculations on a conceptual problem, but they're asking to test a concept and there's no calculation needed. Now, typically, if it's a calculation problem, you're going to have the points broken down as shown here. 2 points for appropriate figure, 3 for getting a correct explanation of the concept you're using, 2 for identifying the correct equations involved, 2 points for doing correct math, and 1 point for the correct answer. Now, some problems won't need a figure. Any problem that doesn't need a figure says in, I just finished making the test before class, says in the description, no figure necessary. There are some that say you don't need to put an additional figure, but you need to make annotations on the one that's given. So pay attention to those instructions. If there's no figure necessary, that the points that would have gone to the figure will go into the concept. So the concept becomes more important when there are things missing. Likewise, in conceptual problems where there's no calculation, those points will be going into the concept. So when points are taken away from something, they go into concept pretty much. Now, of course, people want to know, how do I prepare? What can I use? Well, the best thing, I think, is to look at previous examples. So if we go to the website for the class on Moodle, hopefully I'm still logged in. So yeah, here's the class. Go down to section 3, since this is the section the test is. And the example solution is the solution to a problem I did last year for a student. The equation sheet, so if you click there, I think I missed. If you click on the equation sheet, you'll see exactly the equation sheet that I'm going to give you for the exam. That's all of the equations we have, including a cartoon that's in today's lecture. So that's the entire equation sheet. Now, some people might say, wait, I don't see the Pythagorean theorem. Well, the law of cosines is the Pythagorean theorem, except for it's more generalized than the Pythagorean theorem, which only applies to right triangles. So those are the equations you'll have. And then you can look at exams I've given for a couple different years, 2011, 2013, 2014, last year. I'm just going to go to the solution here from last year. Last year was the first year using this textbook. So the breakdown of what's on the exams is a little different. 2014, you'll see, has force problems, whereas your exam won't. It'll be like this. So here you can see my solutions, how I wrote out the concept, the work, and so on. So you can have an idea of what I'm looking for, how I'm going to be grading. So, look through those, make sure you can do the different types of problems there. There are also, in the Moodle page, if you go to the very bottom, there's a section on review, and it has practice problems from the different exam or chapters. So obviously, chapters 1 through 3 are the ones you'd want to be looking at practice problems for this exam. So just some information on resources that are available that I've put out there to help you in preparation for the exam. Any questions on the exam at this point? They're not raising hands either. Okay, one other statement here, what I have in green. Remember, if you are found with a cell phone in your pocket, you'll get a 0 on the test, right? So just don't have the cell phone in your pocket. You can leave it in the front of the classroom or something like that, but don't have it with you. You'll only be allowed to have a calculator. Change the color, maybe. A calculator, a pen or pencil, whatever you need to write, and ruler, protractor, compass, so that you can make the accurate figures, because you have to draw an accurate figure. That is The length has to be scaled, 1 centimeter is equal to 1 mile or whatever your scale is, and the angle is correct. And of course, I have rulers and compasses and stuff here in the class, but if you have your own, it's easier. You don't have to share or whatever. And of course, I don't have them for the people at Southwestern, so I don't know how you're going to have and what you have available. But those are the only things. We'll supply you with paper to write on and the test. You'll actually do your solutions on separate pieces of blank paper. Yeah, Mahala.
I noticed that the quadratic formula isn't on the equation sheet, so we should know that.
That's a good question. I'll go ahead and just add that on there. Okay.
And also, will we need protractors? Because in the textbook, they mentioned something about protractors.
You'll need to be able to measure angles. And if you don't have one, there's one in the drawer at the end of your table there. The question for people at Southwestern, what she asked was she did not see the quadratic, and I said I'll add that to the equation sheet. Okay, going into material, I'm going to finish talking about trajectories today, solve a couple problems, hopefully not spend the entire time on trajectories, but get into the forces, because today is also supposed to be our introduction to forces. So we ended with this picture, I believe, of a soccer player kicking the ball. I'm trying to get into soccer, so go Man City. I stopped playing soccer when I was in high school and cut my foot and couldn't kick a ball. So one of the important things, the reason we did the whole demonstration with the shooting the ball and hitting the target was to illustrate what we call the independence of motion. When I have a particle or something, like my tennis ball, that's flying through the air, he's taking notes. You can't fault the person for taking notes. I was going to throw the ball to you, Colton. But okay, so I throw it to Colton. It goes up. It comes down. Gravity is what made it come back down. But gravity only is vertical, right? The acceleration of gravity is down. And so there was no acceleration in the horizontal direction. So when we solve problems, we'll break things up into the vertical direction and the horizontal direction for a trajectory. And that way, the acceleration will only be in one of those directions. And we solve it as two completely separate problems, but they have to have the same time. And so time is what ties the two problems together. So, this picture here is showing funny things, but what you're supposed to note is on this trajectory, the horizontal portion, the blue portion here, is the same length for each one of these. But the vertical portion goes up, is 0 at the top, and then goes down. That's changing because of the acceleration of gravity. Horizontal component is staying the same because there's no horizontal acceleration. In fact, when we are doing any kind of problem that has to do with acceleration, you'll want to set your coordinate system so one coordinate is parallel to the acceleration and one's perpendicular. So we'll have problems that we call inclined plane problems, where we have a ramp and something sitting on the ramp, like you had in lab yesterday. And in that case, it can't accelerate into the ramp, but it can accelerate down the ramp. And so you set one component direction parallel to the ramp, the direction it can accelerate, and then the other one perpendicular to that because your components have to be perpendicular. And that way your acceleration is in the direction parallel to the ramp and 0 in the other direction. So let's get into looking at problems. So here's a problem that comes from your textbook. The trajectory of a fireworks shell. You'll have two problems of this type, not this problem, but two-dimensional motion problems on the exam. The trajectory of a fireworks shell. The fuse is set to explode the shell at the highest point in this trajectory, which is found to be at a height of 233 meters and 125 meters away horizontally. The picture is nicely drawn already, so I don't have to draw the figure. On the test, it wouldn't be drawn for you probably, so you'd have to draw a figure something like this. Notice X and Y directions are already defined for me. Now, there are a few things I'm going to add to this figure. Primary among those are the acceleration. So what's causing the acceleration for this firework? Assume, of course, that it's shot from a mortar, so it's not accelerating because of a rocket propelling or anything like that. So what would cause acceleration while it's in the air? Just gravity. In what direction is that? Downward. And so I'm going to have the acceleration, and I'm just going to put is equal to g. Now, that seems really redundant, but I have it there now, so I can look at it and say, ah, yes, I have the acceleration. So I have my figure, all good. What was the next step in solving problems? Our variables, I think is what I heard. So I need to look at my variables, but in this case, I have to do it for two separate directions. So I'm going to split my page and put vertical on one side and horizontal on the other. And so then I look at my vertical direction. What's the initial position in the vertical direction? 0. Okay. So I'm going to use y for vertical because my figure has y showing there for vertical. So y initial equals 0. What about the final for vertical? 233 meters. Now, if I go over to horizontal, what will my initial position horizontally be? 0. And my final position horizontally? Okay, so there's my position variables. Then we go to velocity. So the vertical component of velocity is separate from the horizontal component. I don't know what the speed is, though. So I write and I'm only going to do initial. So the initial velocity in the y direction is equal to my unknown initial velocity. That's the magnitude of my total velocity. But then I can break it up. I have an angle of 75 degrees between the x-axis and my velocity. So if I want to find the vertical component, there's my vertical component. Which side of a right triangle, using that 75 degrees, is the vertical component? It's the opposite side. So here's my v. You can put v0y, vy0. It doesn't matter. It's your symbol, as Bob Ross would say. What's important is that you know what it is and you can use it. So my initial speed in that direction is the opposite side. My v0, my initial speed, is the hypotenuse of this right triangle. So the trigonometric function that relates opposite and hypotenuse is sine. Hence, I know that sine of theta is equal to v0y over v0. Solve it for v0y. It's v0 times sine of theta 0, where theta 0 is shown right there, 75 degrees. So I don't have the number v0 here. So I put the symbol that I don't know what it stands for in the equation. I do know what theta 0 is. What about in the x direction? Which side is the x component? Adjacent, opposite, or hypotenuse? Adjacent. Now, one thing to note is that these components have to add up to give me the full vector. They have to be perpendicular because they're in the two directions of my components. They have to be perpendicular and they have to add up to the total vector. So this is the adjacent side. The trigonometric function that relates adjacent with hypotenuse is cosine. So there's my initial speed. And then I have acceleration in the y direction is equal to minus g, or minus 9.80 meters per second squared. Acceleration in the x direction we said was 0. Why is the acceleration in the y direction negative? Gravity is pointing, looking at the figure, gravity is pointing down, but our y direction is defined as positive up. So that's why it's negative, right? You can look at the picture, it clarifies the signs. The thing that ties these together is the time. They both have, of course, time initial is 0. It pretty much goes without saying. And so I look at these, and what are my unknowns? My unknowns are the initial speed and the time. What does it ask me for? Actually, I didn't put the question, did I? Then we better find both of them. I swear I thought I put the question in right. Okay, let's find both. So I have to decide how I'm going to find these. Well, it's kind of a decision we have to make. Both the x direction and the y direction, I'm going to have two unknowns. And so having those two unknowns, there's some confusion about how to do this. But in the vertical direction, I can think myself out of this box. Because in the vertical direction, I know that what's the vertical speed at the top? 0. So I know at the top the speed is 0. And so I can use my y final minus y initial is equal to Vy final squared minus Vy initial squared all over 2ay. And I can solve that to find, suddenly I have this brain fart. I think there's a T there. I can solve that to find what the unknown is, right? I can solve this to find, see, notice I switched the positions of my final versus y there. Sorry, inconsistency. I can solve this to find the value of Vy initial. And once I find the value of Vy initial, then I'll know what V initial is. So let's just go ahead and do that. Let's do y final. Well, first multiply both sides by 2ay. Obviously, I have to move the minus across, or I'm going to have some problems in my square rooting. So move the minus across, that is multiply both sides by -1. And then square root both sides. And I'll have two answers, a positive answer and a negative answer. Because it started going up, I'm going to take the positive answer. So let's just get that. Vy initial is equal to the square root of -2 times minus 9.80 meters per second squared times the y final, which was 233 meters, minus the y initial of 0. And so we can put down our calculator and calculate immediately what the Vy initial is. And of course, I don't know the number off the top of my head. I'm waiting for somebody to tell me.
$67.578.
67.578 meters per second. Yes, we only have 3 sig figs. I put 9 point, I put the numbers in right. Now, if we look up here, Vy0 is V0 sine of the angle. So now I can find the speed. So this is equal to V0 sine of 75 degrees. So if I divide both sides by sine of 75 degrees, I'll have V0.
$69.962.
69 point what?
962.
To correct significant digits then, that is 70.0 meters per second. So now I've determined that it started at 70 meters per second, and I can use either side now to calculate the time. Which side do I want to use? It really doesn't matter. I kind of feel like the horizontal side has been left out, so I'm going to use it. But I could have done the vertical side just as easily. So now I'm going to have the x final equals x initial plus v initial x t plus 1/2 ax t squared put zeros for the x initial because they start at x. We have it written there. 0 for the acceleration. And I have a very simple equation for time. And now I'm going to use these full digits. And notice I had to use the cosine because I'm talking about the x component for the speed. .90 seconds.
Yeah.
And since there are only 3 significant digits, I won't worry about asking you for more and then rounding to 3. So my time is 6.90 seconds. Now somebody might have said, what if I wanted to use the vertical direction to find time? What's the easiest way? Notice I have a lot of variables. And I said the first way to approach these problems is to look at what variables you have and what you're looking for. But then I kind of had to go with feel. That's why we have homework problems. So you can solve problems enough different ways that you start to get a feel of, oh, this is going to be the quickest way. There are a lot of ways to do things. To find the time now, I could use, my y final equals y initial plus vy initial t plus 1/2 ayt squared and have a quadratic and solve it. Or I could say, well, looking in the vertical direction, vy final equals vy initial plus ayt. And then I would just solve that for t is equal to minus vy initial over a. And in that case, of course, that's actually easier calculation than what we just did. That's 67, excuse me. It's this number right here. And that better give us the same time. If it doesn't, then, we made a royal mistake. Now, another thing to note is, you notice I put the units in on every step of my calculations. I'm not going to mark you off if you don't, but putting in those units allows me to look and make sure that my calculations are making sense in terms of units. If I look, for instance, this calculation for speed, meters per second squared times meter is meters squared per second squared. Take the square root of that, meters per second, correct units. You look over here, time is distance over speed, meters over meters per second. Do the invert and multiply, that's meters times seconds over meters, the meters cancel, units of seconds. Right? I write those units in there so I can verify that I have the right units. So obviously the homework that's due Friday is going to be problems like this. I'm going to do one more, but any questions on how I solve this? Okay. What question back, Joel?
Is this going to be on Moodle?
Yes, indeed. Where in Moodle it has the lecture presentations, right? You click on that, and right now you can see what I have, but without my annotations. And after class, I save it, and it just replaces it with updated with the annotations. So the question was, is this available on Moodle? What I'm doing here, the lecture notes, yes, it is. Okay, next problem. This problem is a little harder. How far from the volcano does the rock land? The rock shoots out of the volcano. It gives us the initial speed and the angle, and it tells us it lands at a height of 20 meters below where it started. So since we've just worked one problem out, what do I need to do to work this one out? What's the first thing I need to add to the picture? The what? Acceleration. I need to add the acceleration. So I have here, the acceleration is going down. Then I need to know which thing. the variables. Now, if you were solving this problem on the test, the first test is the easiest one for concept because for this, we're saying it's two-dimensional using the kinematic equations. That's about all you need for the concept here, right? It's very simple. Later on, we'll have forces and this and that. And you'll have a lot more ideas you have to put down. So I am once again going to break it up into my x component, my y component. So keeping vertical on the left and horizontal on the right. I am going to have then that my x initial is equal, or y, excuse me. Y initial equals, and I kind of have to make a choice. Do I want to make the top of the volcano 0 or where it lands 0? It's a choice anyone can make. So somebody blurt out. Where it lands. Okay, so we're going to make where it lands is 0. So that means it starts 20 meters above that. So it's going to start at 20 meters. Let's assume that's two significant digits since it's ambiguous. The y final then is 0. For the horizontal, there's our position information. Now let's go to the speed. So now I put y0 instead of 0y. The initial speed in the y direction is equal to, and how do I break that the velocity vector into its components? I use sine and cosine. So I will draw in here, not with that color. I will draw in the components once again, they have to add to give me the total vector. So that's why the first one starts at the beginning and has its arrow at the right. The second one starts at the arrowhead and goes up to the end. So for the vertical, that's the opposite side. And so that's going to be opposite side sine. So what's 25 times sine of 35 degrees, just to get it out of the way? 14.34?
Yes.
Okay, 14.34 meters per second. In the horizontal direction, we're looking at the adjacent side, so that's going to be using cosine. And what do we have for that?
20.48.
And actually, can you give me one more decimal point for the
478.
actually for the vertical? It's what?
3 or 4.
Okay. Just so we don't throw away information before we get to the answer, we want to keep at least one extra digit beyond our significant digits. There's 2. That makes me feel better. Okay, so I have my initial vertical and horizontal speeds, my initial and final positions. All I have left is acceleration in the y direction, minus 9.80 meters per second squared. Acceleration in the x direction is equal to 0. And the thing that ties them all together So now I look at this, and this is more standard, really. Just look at the number of question marks. How many question marks do I have on the vertical side? 1. How many do I have on the horizontal side?
2.
Which side do you think we should start with? The vertical, because it only has one unknown. One equation, one unknown. You can solve it right there. You don't have to do anything fancy. So we're going to start with the vertical side because it has one unknown. And so I have which variables involved? All of them. Since I have all the variables involved, which kinematic equation am I going to use? The one that has all of them. So I will use y final equals y initial plus vy initial t plus 1/2 ay t squared and solve that for time. Now here's an unfortunate thing in terms of time spent in class. If I'm going to solve this, I have a quadratic. Quadratic's no fun. So you know what I'm going to do because I don't want to use the quadratic? I'm going to do two separate calculations instead. What are those two separate calculations going to be? One, I'll use the equation without time to find the final vertical speed. And then once I have the final vertical speed, I'll use the equation that relates speed, acceleration, and time to find the time. That's a way of getting around having to use the quadratic. That's what I basically ended up doing on that test I told you about. So instead of using this that would have given me the answer in one shot, but had me use the quadratic, I'm going to use this and solve it for Vy final. So I had to multiply both sides by 2ay, and then I had to add Vy0 squared to both sides to get this. And then I just, of course, square root both sides. And I have Vy final equals plus or minus, because there's two answers when you have a square root. So what do I get for that final speed in the y direction?
20.16.
And then once I have that, I will use the equation that...
It's going to be negative.
Okay, yes. There are two answers. It's plus or minus, and which one is it? Because it's going down, it has to be the minus one. Thank you for pointing that out. So Vy final is equal to Vy initial plus Ayt. Therefore, time is equal to Vy final minus Vy initial all over Ay. And you can see if I had not paid attention to Jonathan, if I had not corrected my sign, I would have got a wrong answer here. So you do that, that's what, 34.50 divided by 9.8.
3.52 seconds.
Can you give me one more digit?
520.
Now, what's significant is only the 3.5, but I want the 3.520. So I can come over here to the x direction and say, aha, x final is going to have to be x initial plus Vx initial t plus 1/2 ax t squared. Ax was 0. X0 was 0. So that's just going to be and so we can find the final distance it travels, which I think was the question it asked for. So going out on a limb, it's somewhere around 70, just a little over 7.
72.09.
And I'll just leave it at 72 here because it's my final answer, and I only have two significant digits. On your exams, make sure that you honor significant digits, okay? Even on the problem, there will be one problem that's a significant digits problem on your exam. Even on the others, make sure you pay attention to significant digits in your answers. Okay, so do we have questions about that solution? Yes, Paris. Any other questions about the solution? Brady.
Those problems are only looking for
Let's go back to the beginning. How far? Yes. Yeah, okay. That is an interpretation. How far away, we generally mean what is the horizontal distance. But you're right, there is actually a hypotenuse to be found if you take the horizontal and the vertical. And hopefully I don't have problems that have that possible, different reading. But on the test, of course, if you have a question, ask me and I will clarify. That's what the teacher's here for, is to clarify questions during an exam. And if in the end you had a very reasonable and sensical interpretation that was different from the intended interpretation, I'll still give you credit because I'm grading on your work. So if you had said, if you got this number and then you said, so the hypotenuse is, and you found the hypotenuse, I certainly wouldn't have marked you wrong. Right? Because that would not be showing a lack of understanding. Okay, going to the next slide. This is actually my last slide in the trajectories. You can change the distance traveled by changing the angle. We saw that with the motorcycle example last Wednesday. Changing the angle. What angle made the motorcycle travel the farthest? 45 degrees. That's not always true, though. First of all, you have to have no air resistance for that to be true. And no air interactions completely, as we'll see. Actually, there's one more slide trajectory I just remembered. But second, it has to start and end at the same height for that to be true. So let's say you're playing basketball. I can't play basketball to save my life. But if I could, I was out there playing, I'm shooting. What angle do I want to shoot at, do you think, to get the optimal range? That is, I have to have the lowest speed coming out of my hand when I'm shooting a basketball. What do you think that angle is going to be?
It's going to be probably around 75.
Okay, about 75 from the horizontal. Any other answers there? Okay, I heard somebody say 30. What did you say, Jordan?
Greater than 45.
Jordan says greater than 45. Well, when I was in college, I'm into all sport, even if I can't play them. I read an article where a physics professor sat down and he calculated 3 different things. Number one was which angle gives you the best distance for shooting. The next, that's the simple one. You could calculate that one right now if you actually sat down and thought about it. Second one was which one gives you the most margin for error in terms of how hard you were shooting. Like if you shot a little too hard or a little too soft, which gives you the biggest margin of error. The third one was biggest margin of error for angle. And all of them came out to be the same thing. And that angle was the angle that would make the ball be traveling at 45 degrees when it hits the height of the rim. So since you're shooting from below, it's going to have to be steeper than 45 because you're going up. The vertical component is getting smaller, so the angle is flattening out. And so Jordan had the best answer that I could have given, somewhat steeper than 45 degrees. And it depends on how high your release point is, what that angle is going to be. If you're tall enough that your release point, you're like Manute Bol and you're shooting with your arms straight up above you, it would be pretty close to 45 degrees. Manute Bol may not be the tallest player that's ever played, but he was when I was in college. Okay, my last slide, reality versus general physics. This is reality for baseball. If you look at reality for golf, it's much more interesting, actually. I'm not going to work out this problem. We've done 2 problems already. But if you have somebody that hits the ball starting, a half meter off the ground, so obviously they're not standing straight up like I am. They're down, they're crouched. It comes off the bat with a speed of 49.2 degrees at an angle, or 49.2 meters per second, angle 42.5 degrees above horizontal. How far does it go? That's a calculation you can do for general physics, and the answer you will get will be 571 feet. But if you're actually playing baseball and you exactly replicate it, you're only going to get 397 feet. Why the difference? Air resistance. And it's interesting to note that air resistance actually makes it so it goes above the trajectory it would have if it didn't have the air resistance. But it also goes much shorter. Question from the front.
Are there any vacuums that are designed, that large where you can test things?
There actually are the chambers where they make satellites. They have huge vacuum chambers that are like big warehouses. Maybe not 397 feet, but they have really big. But I don't think they use them for things like this. They do things like the classic experiment. You can watch a YouTube video of it being done on the moon, where you drop a hammer and a feather at the same time. Now, if I were to do that here on Earth, you would see exactly why Aristotle said, well, the feather has more air in it and less earth, so it doesn't want to be on the ground as quickly, so it falls at a nice leisurely pace. Whereas the hammer has a lot more earth, it wants to be on the ground much more, and so it falls quicker. You would see that if I did it right here in front of you. But if you do it on the moon or if you do it in a vacuum chamber, they fall and they hit the ground at the same time. Because the air resistance makes a huge difference for the feather, minimal difference for the hammer. So yes, they do make big chambers. I don't think they use them for something like this. Now, in sport, there is a lot of science that goes into it. So golf balls, they have those dimples because the dimples kind of grab air, and as it spins, you have air spinning with the ball, and then you have air on air friction, which is much less than air on the plastic or sirloin or whatever the cover's made out of. And so it decreases the air resistance. But also, because of the spinning, you have a lower pressure on top and a higher pressure on bottom, which makes the golf ball go higher. And so the trajectory of a golf ball, that you hit them kind of flat, and the trajectory goes something like that. And it goes like 3 times farther than it would if there was no air, right? You're taking your energy, you shoot it flat, so you're putting as much energy as you can into horizontal speed, and then the spinning converts some of that into vertical, making it go higher, staying in the air longer so it can go more distance, and then drops it pretty flat so it doesn't have a lot of run. So if you drop it on the green, it stays on the green ideally. That's, of course, assuming you got backspin on it. If you can't golf like me, no. Even if it hits the green, it's going to go 500, not 500 feet. That would be a monster drive. But it's going to go 50 feet beyond the green just because I got no backspin. Okay, so there's a lot of physics that comes into play in real life sports, but our general physics approach is only giving us kind of the ballpark range. And by ballpark, you can see here, within 30% for this batted ball. So when things are going faster, there's bigger deviations from our general physics solution. So it's always important to understand, we've made some approximations. You probably heard the silly jokes about an engineer, a physicist, and a mathematician calculating how long it takes for a chicken to fall. And the engineer goes into all kinds of detail. You get finally to the physicist, and he says, well, assuming a spherical chicken, and makes approximations, throw it all away, and it's not going to be very realistic, but it gives you a ballpark idea. Okay, our first of our clicker questions, give me a second to advance the slide. Okay, you can answer now. What variable ties the vertical and horizontal motion of a trajectory together? Okay, give it about another 10 seconds here for people to get their answers in. All right, our final answers are 6, 16, 2, 25, and 2. So that's no majority, but there is a strong plurality. So rather than having people discuss, because we only have 5 minutes left, I'm going to go through the answer. I'm not even going to pull a card here. The correct answer here, from my perspective, is time, because they both have the same time. But I can see a good call for answering velocity as well, because the velocity, it's one velocity, but we broke into two components, and so that also is tying them together. So I can see that. The reason I choose time is because usually when we're solving it, we do like we did in that last problem where I used the vertical axis to find the time, and then I used that with the horizontal direction to find the distance. And now we turn to forces. In 1687, Isaac Newton published his book, Philosophiae Naturalis Principia Mathematica, or as we usually just call it, Principia Mathematica. I've never read it because I've got the attention span of a gnat. But I am told that it's actually pretty hard to read. It's not one of those books that flows and makes sense to most people. But it lays out his incredible work, mostly that was done during that time when there was no school because of the Black Plague. And so in it, he lays out his 3 laws of motion that we're going to be talking about in just a few moments, and gravitation and things like that. So everything he was doing was really looking at forces. Forces are anything that push or pull. So Colton has my ball. Colton can take that ball, he lifts it up, he throws it, he put a force on it, he pushed on it when he threw it. That's what a force is. This picture shows what we had in lab yesterday. You had a cart, okay, so it had some wheels on it. And on that cart, you had forces. You had those 3 forces that are shown. Now, I haven't defined them yet, so let me wait until I get to what the forces are so we can define them. But that's what we're going to be talking about, forces, things that push or pull. And so there are 4 fundamental forces that we know of in physics. I read an article just a week or 2 ago that was proposing there might be 1 or 2 additional forces that they're learning about at CERN. A very vague proposition. But these are the 4 fundamental forces that we know of. There's the gravitational force, which is an attractive force that pulls everything toward everything. So I always use people as examples. There is a force pulling you toward every other person in the classroom. That's a gravitational force. It's generally the weakest of all the forces. But like in astronomy, it's ultimately the strongest. It's the most important one, in my opinion, in astronomy, because it's the thing that's holding the planets together so they don't fall apart, holding planets in orbit about their stars, holding stars in orbit about, the galactic center. It's all about gravity there. The reason it's all about gravity and the gravity dominates in large is because gravitational force is always attractive. The second force here, the weak nuclear force, it's only important inside a nucleus. You have to have very, very close together hadrons. The strong nuclear force, the strongest of the force, also is only important inside nuclei. You have to have, once again, hadrons that are very close together. And then there's the electromagnetic force that's in between. The electromagnetic force is another one that we deal with all the time. But electromagnetic force can be attractive or repulsive. Like charges repel. That is, 2 positive charges push each other apart. Opposite charges attract. This one doesn't dominate on large scale because you tend to put in about equal numbers of positive charge and negative charge. So on large scale, this goes towards 0 simply because your total charge goes towards 0. These 2 here, by the way, in case you've ever heard it, are combined into what's called the electroweak force. So physicists have worked to try to combine these forces. The goal is to have one force that this is just different aspects of, and they've been able to combine those 2. Common forces are listed over on the right. Your weight is a force. It's you pressing down on the earth, and it's caused by the force of gravity. Normal force is a force of a surface keeping you from going through it. So right now I'm standing on the ground, and I'm not going through the ground. I'm pushing down but not going through. So the ground has to be pushing up to keep me from going through, and that's the normal force. Tension, well, actually, let's talk about the rest later because I have to get to Newton's 3 laws, because one of your homework questions is about Newton's laws. Newton has 3 fundamental laws of motion. The first one is called the law of inertia. Inertia is the propensity of something to stay in constant motion. Constant motion means constant velocity, no change in speed and no change in direction. And so that law of inertia says an object remains in constant motion unless an unbalanced force acts on it. Does anybody know how you measure inertia? Mass. Mass is the measurement of inertia. The second law is the one that has this equation. You often see people write it as F equals ma. The order there is fine, right? You can solve it however you want, but it's wrong because you really need to have either force net or a summation sign. It's the net force acting on an object is equal to its mass times the acceleration of that object. This one here is the one that we're going to be doing a lot of work with in the coming week. And then the third law says for every action, there's an equal and opposite reaction. In this statement, action means force. So for every force, there's an equal and opposite force. That means that if I am so stupid as to punch the wall, I got to be careful I don't damage it, like I did when the Raiders lost that game in New England many moons ago. Punched a hole in the wall of the condo we were renting. When I punch the wall, I put a force in the wall, but it has to put an equal force in the opposite direction back on me. You had a question, Rachel?
Is that supposed to be negative 12?
Yes. The force of 1 on 2 is equal to minus the force of 2 on 1. Okay, we're out of time, so I will start up with this, but I had to get it in there because you got a homework question on it. So remember, homework is due before sundown. I believe it's 7:35 on Friday evening. There's a homework due today as well, but you might have got the Friday early.